Hello students. So in the last class, we had studied about UDP, User Datagram Protocol, which is a connection-less protocol. In connection-less protocol, there is no guarantee of the delivery of the packets between a sender and receiver. So in today's session, we will be studying about TCP, Transmission Control Protocol. It is one of the most widely used protocol for data transmission in communication networks. For instance, the internet. Also, you all are aware that TCP is a connection oriented protocol where there is guarantee of the delivery of the packets between a sender and receiver. TCP provides process-to-process communication with the help of port numbers. So if you see in this diagram, TCP is a connection-oriented protocol that provides a reliable unicast end-to-end byte stream over an unreliable network. So process-to-process communication takes place as TCP resides in the transport layer, and it provides a reliable unicast end-to-end byte stream over an unreliable network. So you can see in this figure, there is an incoming byte stream that passes through TCP, and from that it passes through an unreliable internetwork or an IP internetwork, and from here what happens in that case is your TCP packets which are there, they are passed through your TCP at the receiver's end, and your byte stream is obtained after passing through TCP at the receiver's end. As I told you, TCP is a connection-oriented protocol. Before any data transfer, it is very important that connection gets established. We have also seen in our practical, when we were performing socket programming, the connection needs to get established first, then only we are able to send the data or information. So one TCP entity is waiting for a connection, that is nothing but your server. The other TCP entity, that is the client, contacts the server. The actual procedure of setting up connections is comparatively complex. It uses different transport layer service primitives for setting up the connections, like your bind method or bind service primitive, accept, listen. These are the different primitives that are used. And the connection is full duplex. Duplex means two-way, and full duplex means client to server and server to client. So you can see in the diagram over here, the client is sending a request for a connection to a server. Then the server is getting that connection request. The server accepts the connection request and notifies this to the client. There is data transfer taking place between a client and the server once the connection is established. And finally, the request for disconnecting the communication between client and server is initiated. These are some of the features of transmission control protocol: process-to-process communication. Port numbers are used to carry out communication. If you remember in the practical, we had used the port number 8080. which is for HTTP. Using the bind service primitive, we were basically trying to bind the host address and the port number. Numbering system. Now what does this mean? Your TCP keeps track of segments that are received or transmitted. It also keeps a track of the byte number, sequence number, to be precise, segment number. We use the concept of sequence number in your network layer. Transport layer, the terminology used is segment number, and finally the acknowledgement number. So TCP keeps a track of the byte number, sequence number and the acknowledgement number that are being sent or received. It also considers flow control, a reliable error control, and considers congestion control. So these are certain features of TCP. So now let us see what do you mean by reliability. As we all know, the main focus of your transport layer is to ensure reliability. So your byte stream is broken up into chunks. Okay, those chunks which are there, small groups, they are called as segments. So receiver sends acknowledgements for the segments that it receives from the sender. TCP maintains a timer. If an acknowledgement is not received in time, the segment is retransmitted. So here the timer has a full control over the acknowledgement. It has to be received within the specified time. If the acknowledgement is not received within the specific time, then the segment is retransmitted. Detecting errors. TCP uses checksum for detecting errors that could be present in the header field and the data or payload field. Segments with invalid checksums are discarded. Each byte that is transmitted has got a unique sequence number, which helps in easily detecting errors. So here are certain TCP service models. TCP provides applications with a reliable byte stream between processes. As I mentioned, it is process to process communication. So a reliable byte stream is provided to applications by TCP, and the popular servers that run on the well-known ports are specified below. So we have got port number 2021 for FTP if you want to transfer a file transfer protocol. Port number 22 for SSH, that is remote login, or currently it is a replacement for Telnet. For SMTP, simple mail transfer protocol, port number 25 is used. Port number 80 is for your World Wide Web, which uses HTTP protocol. We have got POP3, that is POP3 for remote email access with port number 110. For remote email access, we also have got IMAP with 143 port number. Secure web, HTTPS, we should use port number 443. For media player control, you can try RTSP with port number 543. And for printer sharing, we use 631 as the port number, which involves the protocol IPP. So applications using TCP see only the byte stream and not the segments. Byte streams are over here, as you can see towards the right hand side. They are not concerned about the segments that are sent as separate IP packets. So you can see in the figure over here, we have got 4 segments A, B, C and D. Each are of 512 bytes of data and carried in an IP packet. That is why you have got this gray color shaded portion as the IP header, and within that you have got the TCP header. So these 512 bytes which are there all are merged together, which is 2048 bytes of data delivered to an application in a single read call. So applications that are using TCP, they only see the byte stream and not the segments as your separate IP packets. Next, we move on to your TCP format. This topic is very important from your examination point of view. TCP segments have got a 20 byte header. So you can see over here, we have got TCP header which is of 20 bytes. And then you have got TCP data or TCP payload field. Now, if you see over here, 20 bytes, how it has been basically included. We have got your source port number, destination port number, sequence number which is of 32 bits, acknowledgement number which is of 32 bits, length of the header, flag field, window size, TCP checksum, urgent pointer, optional field and the data field. The source port number is of 16 bits and the destination port number is of 16 bits. So overall 20 bytes are allocated for your TCP header, like your IP header. So let us see in detail the explanation of your TCP header. As you can see, the TCP header can have a varying range of 20 to 60 bytes, and a packet in TCP is called a segment. As I mentioned, in network layer we use the keyword packet, whereas in your transport layer we use the term segment. So we have got source port address which is of your 16 bits, destination port address which is of your 16 bits. So you can see here there are two applications, application 1 and application 2. We have got the source, which is the client, you can say, using a specific port number for an application, and we have got application 2 which is the server using a specific port number. Sequence number which is of 32 bits, it basically means number assigned to the first byte of the data. Okay, and sequence number plus 1 will be called as your acknowledgement number which is of 32 bits. Then we have got HLEN which is the header length which is of 4 bits. We have got a reserved field which is of 6 bits used for future purpose. Then we have got certain other fields. URG stands for urgent, ACK stands for acknowledgement, PSH stands for push, RST stands for reset, SYN stands for sync, and FIN stands for finish. So these are different fields that are present. Window size is of 16 bits. And what is its purpose? It is used for sending TCP in bytes. For error detection and correction, we use checksum, which is of 16 bits. And we have got urgent pointer, which is of 16 bits, and it is valid only if the flag is set. This is your flag field, your entire field which is there over here, which I told you, acknowledge, push, reset, right? So it is your flag field, then only your urgent pointer becomes valid if the flag field is set. And finally, we have got your options and padding field. So TCP segment header. TCP header includes addressing, which is done through the ports, sliding window, which uses sequence and acknowledgement number, flow control, error control, and many more things. You can see the format of TCP segment header as I showed you in the previous slide. It is having a variable size of 20 to 60 bytes followed by the data field. So you can see over here 0 to your 31. Okay, total number of bits. So this should basically be from your 0 to 31 or 1 to 32. This is the correction, and these are the same fields what I've explained it to you in the previous slide. So let us explore each of these fields in detail, as this is an important question from examination point of view. The source port address, which is the first field. This is a 16-bit field that defines the port number of the application program in the host that is sending the segment. This serves the same purpose as the source port address in UDP. So we had already seen in UDP, we have got a UDP source port address. The same functionality is provided by the source port address under TCP header. That is a 16-bit field defining the port number of the application program in the host. Similarly, we have got destination port address. Once again, a 16-bit field that defines the port number of the application program in the host that is receiving the segment. We have got sequence number, a 32-bit field that defines the number assigned to the first byte of the data, okay, contained in the segment. So within the segment, when the first byte of the data is considered, we assign the sequence number. TCP is a stream transport protocol. To ensure connectivity, each and every byte which is to be transmitted is numbered. The sequence number tells the destination which byte in this sequence is the first byte. If we don't have a sequence number, then it is very difficult at the destination to identify in a particular segment which is the first byte. So this entire process is simplified with the help of the sequence number. During connection establishment, each party, that is the client and server, uses a random number generator to create an ISN, which is an initial sequence number, which is usually different in each direction. Then we have got acknowledgement number. This is a 32-bit field that defines the byte number that the receiver of the segment is expecting to receive from another party. So 32-bit का field है that basically defines the byte number that the receiver is expecting to receive from another party, which is the sender. If the receiver of the segment has successfully received the byte number, then what does it return? +1. So as we saw, sequence number is denoted by X. So acknowledgement number will be what? Sequence number +1. That is X plus 1. Acknowledgement and data can be piggybacked together. You know what is piggybacking? You temporarily delay the acknowledgements and at one go you send all the acknowledgements. That is called as piggybacking. Next we have got header length, which is of 4 bits. It indicates the number of 4-byte words in the TCP header. The header length can be between your 20 and 60 bytes. Therefore, the value of this field is going to be between 5 and 15. So keep this in mind. This is of your 4 bits. Because we have got TCP header having a variable size of 20 to 60 bytes, the value of this header field will lie between 5 and 15. We have got the reserved bit, which is a 6-bit field included or reserved for future purpose. Then we have got the control field, or you can call it as the flag field. It defines 6 different control bits or flags, as you can see in the figure, and each of these bits can be set at a time. And what is the functionality of these bits? They enable flow control, connection establishment and termination, abortion of a connection, and the data transfer mode in TCP. So you can see the first field that you have got is URG. That is urgent pointer is valid. URG stands for urgent. ACK acknowledgement is valid. PSH request for push. RST to reset the connection. SYN to synchronize sequence numbers. FIN to terminate the connection. It is a 6-bit field. URG, ACK, PSH, RST, SYN and FIN. So what is the use of this particular control bit or flag field? To enable flow control, connection establishment, termination, abortion, and the mode of data transfer in TCP. Coming to window size, this particular field defines what is going to be the size of the window of the sending TCP in terms of bytes. So length of this field is 16 bits, that is the window size, which means that the maximum size of the window will be 65,535 bytes. And this window size ka value is normally referred to as the receiving window, and it is determined by the receiver. So window size is of 16 bits, which is normally associated towards the receiver side. And what happens in that case? The maximum size of the window is 65,535 bytes. We have got TCP checksum, which is a 16-bit field. However, the use of this checksum in UDP is optional. TCP checksum is mandatory over here. The same header that is serving the same purpose is added to the segment. So TCP checksum is basically for error detection and error control. The same functionality is used. The value of this protocol field is 6. Then we have got urgent pointer. Once again, it is a 16-bit field, and this urgent pointer is only valid if the flag field is set when the segment contains urgent data. It defines a value that must be added to the sequence number to obtain the number of the last urgent byte in the data section of the segment. So what does this mean? Urgent pointer is only valid when the flag field is set. If the flag field is not set, okay, for example, if all these are 0, then urgent pointer does not have any importance. But if these are set to 0 and 1, for example, if ACK, sync and fin are set to 1, then urgent pointer is valid. Otherwise, it is invalid. As we all know, sequence number, if we denote by X, acknowledgement number is X plus 1. So if the urgent pointer is also included, then what happens in that case? The value of this pointer is added to the sequence number to obtain which are the urgent bytes in the data section of a segment. Optional field, it can be up to 40 bytes, which can contain additional optional information in TCP header. Now let us see TCP connection management. As you all know, we have studied three-way handshake. Transport layer uses three-way handshake. So TCP connection management also takes place with the help of three-way handshake. This is how the connection gets established. So if you see in this figure, what is happening is the client sends a sync segment, I would say, to the server having a sequence number 6000. What the server does? The server sends the sync segment plus the acknowledgement segment. As we all know, sync plus 1 represents acknowledgement. So what is going to happen over here? This sequence number which is sent by the server is basically 10,000. But acknowledgement is of this particular sequence number. That is why it is 6000 plus 1, and so it is 6001. And this is basically called as the receiving window, which is 5000. Now what is going to happen over here? The receiver sends this to the sender, which is the client. The client now sends an acknowledgement. So sequence number is going to be 6000, but acknowledgement is now going to be sequence number of the second stage, that is 10,000 plus 1, and that is why the acknowledgement is your 10,001, and the receiving window is having a value of 6000. Once this three-way handshake is successfully established, that is, connection has been established, then only data transmission takes place between the client and server. So in TCP, the connections are established using three-way handshake technique. TCP connection management includes TCP connection establishment and TCP connection release. So one point that you have to keep in mind is Acknowledgement number is sequence number plus 1, and you have to see where we are adding that plus 1 in which case. So this is the same thing that is explained where we have got a normal case and a simultaneous connect. So sync request is sent with sequence number X. यहाँ पे sync request is received with sequence number Y, but acknowledgement is X plus 1. And here again it is sent with your sequence number X plus 1 plus acknowledgement Y plus 1. What is happening over here in a simultaneous connect case? Sequence number X is sent with your sync segment, and here sequence number Y is received. Then what is happening basically? Sequence number Y and sequence number X plus 1 is sent. And then sequence number X and acknowledgement Y plus 1 is sent. So this is the normal case that happens in TCP, but there is another case that is called as simultaneous connect, where the release is symmetric. So TCP sets up connection with the three-way handshake. Release is symmetric. So normal case and the simultaneous connect case between the client and server or host 1 and host 2. So let us see the entire process of this particular figure. To establish a connection, one side, say the server, passively waits for an incoming connection by executing which primitives listen and accept, either specifying a specific source or nobody in particular. The other side, that is the client side, it executes the connect primitive by specifying the IP address and the port number to which it wants to connect, the maximum TCP segment size it is willing to accept, and optionally some user data, for example a password. The connect primitive sends a TCP segment with the sync bit on, that is SYN 1 ho jayega, and ACK bit off, that means ACK will be 0, and waits for a response. When this segment arrives at the destination, the TCP entity over there checks to see if there is a process that has done a listen on the port given in the destination port field. If not, it sends a reply with reset bit. So यहाँ पे reset initially 0 था, अभी 1 हो जाएगा on to reject the connection. If some process is listening to the port, that process is giving the incoming TCP segment. It can then either accept or reject the connection. So normal case is shown in figure A. This is like your normal case. Okay. In the event, two hosts simultaneously attempt to establish a connection between the same two sockets. The sequence of events is illustrated in figure B. So if there are two hosts that are simultaneously trying to establish a connection, then the simultaneous connect case occurs as shown over here. The result of these events is that just one connection is established, not two, because connections are identified by their endpoints. As I told you, what is socket programming? It is one endpoint of a two-way communication over a network. So if two sockets are available and two hosts are trying to establish connection, then one of them will get connected, not both. This is for TCP connection release. TCP connections are full duplex. Each simplex connection is released independently of its sibling. To release a connection, either TCP segment, okay, can basically set the fin bit, that is the finish bit, to terminate the connection to 1, which means it has no more data to transmit. So अगर और कोई data transmit करने के लिए नहीं है, then basically what will happen, we set the fin bit to your 1. When the fin is acknowledged, that direction is shut down for new data. Data may continue to flow indefinitely in the other direction. However, when both directions have been shut down, connection is released. Normally, 4 TCP segments are needed to release a connection. 1 fin and 1 acknowledge for each direction. So, to release a connection, you require 4 segments. 1 fin, 1 ACK for each. Okay, so 2 plus 2. However, it is possible for the first ACK and second fin to be contained in the same segment, reducing the total count to 3. So to release a connection, you require 4 or 3 TCP segments. To avoid the two-army problem, we have already studied two-army problem, we make use of timers. If a response to a fin is not forthcoming within 2 maximum packet lifetime, you know what is the maximum segment lifetime, isn't it? 2 into T, where T is 120, 2 into 120 is 240. The sender of the fin releases the connection. The other side will eventually notice that somebody seems to be listening to it anymore and will time out as well. While this solution is not perfect, given the fact that a perfect solution is theoretically impossible, it will have to do. In practice, problems do arise when TCP connection release takes place. This particular slide shows the points of difference between UDP and TCP. So let us see what are the points of difference. UDP is simple, high speed, and it has got low functionality. TCP is full featured, reliable data transfer. UDP is connectionless, TCP is connection oriented. The data interface to the application in UDP is message based data is sent, whereas in TCP stream based data is sent. UDP is unreliable because there is no concept of acknowledgement. TCP is reliable because there is concept of acknowledgement involved. Retransmission is not performed in UDP. If the data is lost in TCP, then retransmission occurs. Flow control not possible in UDP, but in TCP, flow control can be done with the help of sliding window protocol. Overhead is very low in UDP. In TCP, the overhead is low, but it could be high when compared with UDP. Transmission speed is very high in UDP, but in TCP it is low when compared with UDP. The applications that use UDP are DNS, DHCP, SNMP, which are some of the multimedia applications. TCP is used by applications like FTP, Telnet, SMTP, HTTP, etc. Thank you.